Hello everyone. I'm Yuze Wang from Beihang University. It's my pleasure to present our work. Look at the sky-aware efficient 3D Gaussian splatting in the wild. Reconstructing 3D scene from photo collection and achieving photorealistic novel view synthesis remain a long-standing challenge in computer graphics and computer vision, playing a crucial role in virtual reality. NeRF and its extensions represent scenes as radiance fields, significantly enhancing the quality of scene reconstruction and novel view synthesis. Recently, 3D Gaussian splatting utilizes millions of explicit 3D Gaussians to represent a scene, further accelerating convergence and rendering in real time. However, capturing and modeling outdoor landmarks, such as the Notre Dame de Paris, are challenging due to the difficulty of obtaining consistently lighting conditions, and unoccluded photos required for high-quality 3D reconstruction. To address these challenges, several work have extended the applicability of NeRF and 3D using large-scale internet photo collections to reconstruct outdoor landmarks. These unconstrained photo collections available online consist of numerous images of a given scene, each varying in viewpoint, camera settings, lighting conditions, occlusions, and other factors. NeRFW first used generative latent optimization techniques to learn an appearance embedding for each image, to handle appearance variation. Subsequent work, such as HANA-RF and CRNA-RF, have extended this approach by training an appearance encoder from scratch, leveraging deep learning networks such as attention modules and convolutional neural nets. To distinguish and handle transient occlusion present in each unconstrained image, the above work also involve learning per-image transient masks from scratch. Most recently, some initial works have adapted 3D-GS to reconstruct 3D outdoor scenes using unconstrained photo collections. Similarly, they employ networks to learn appearance embeddings and transient occluder masks for each image. Let's review how to adapt 3D Gaussian splatting to unconstrained photo collections. The key components are the appearance encoder and transient predictor, which predict the appearance features and 2D transient masks for each unconstrained image, respectively, and inject them into 3D Gaussian splatting. On the other hand, 3D representation, proposed methods still follow the vanilla 3D-GS approach, optimizing each parameter in the Gaussian. However, during training, they are jointly optimized in an end-to-end manner. This leads to some issues. Optimizing both the transient occluder mask predictor and appearance encoder simultaneously requires more iterations, while 3D-GS typically converges quickly. The mismatch in convergence speed between these components creates a training bottleneck, hindering the overall reconstruction efficiency. This prompts a compelling reconsideration. Can we simplify or omit certain modules, or leverage image intrinsics and semantics as priors to improve reconstruction efficiency, or even enhance reconstruction quality? The inspiration for our work comes from two observations. First, we find that in 3D Gaussian-based in-the-wild scene reconstruction, the transient mask for each unconstrained image can be obtained with a pre-trained semantic segmentation network. No need to retrain or fine-tune the transient mask predictor. By using a simple yet efficient greedy supervision strategy, this approach not only reduces the number of parameters that need updating but also resolves the ambiguity between the 3D radiance field and the 2D transient mask, improving training efficiency. Second, we find that in-the-wild scene reconstruction should place greater focus on the sky. The sky generally exhibits consistent types of radiance, such as black at night, blue during the day, brilliant orange at sunset, with minimal variation across locations at the same time. The mean radiance changes of the sky at different times are relatively small, as shown in figure. In contrast, building exhibits significant radiance variance across locations within the same time and show larger mean and variance of radiance differences across different times compared to the sky. Their radiance transformation properties differ, necessitating different treatment during reconstruction. Now, we explain our proposed approach in detail. Given an unconstrained image, we first pre-process the image using a vision segmentation network, dividing it into three parts: buildings, sky, and others. The others are considered transient occluders. Unlike previous methods, we no longer predict the transient mask through learning-based methods. Then, we use the building encoder and sky encoder to extract features for the sky and building separately. This can be seen as an attention mechanism, allowing the neural network to focus on distinct parts of the image. Next, we propose the Neural Sky module, which generates diverse skies based on the sky embeddings and a learnable implicit cube map. The implicit cube map effectively prevents catastrophic forgetting in the neural network, and we use a TV loss to prevent the generated sky from being overly high frequency. To allow our method to model the scene's appearance from any given cube map, we employ a fine sky encoder to further extract sky features from the explicit sky cube map. Next, we introduce the neural in the wild 3D Gaussian representation to model the 3D building structure. In our modified 3D GS, we assign a trainable feature to each Gaussian. Through an MLP, we combine the sky embeddings, building embeddings, and each Gaussian's feature to transform them into image-related appearances. This results in an explicit, standard 3D GS representation, which retains the excellent performance of 3D GS during rendering. Finally, we observe that the sky color is usually fixed and closely related to the appearance of the building. To leverage this, we propose a mutual distillation constraint that allows the building encoder and sky encoder to learn from each other. Finally, by using the vanilla 3D GS rendering and optimization pipeline, we achieve the reconstruction of 3D GS in unconstrained images. After training the model, we support three types of real-time novel view and appearance rendering, from the unconstrained image level, the implicit embeddings level, and the explicit cube map level. Now, we compare our result with SOTA methods on phototourism dataset. Our method not only reconstructs the sky with greater accuracy, but also captures building details more precisely. We show more comparing results on the RFOSR dataset. We conduct various ablation studies on what contributes to our rendering quality, the influence of using neural sky, ablation study on pseudo-semantic mask quality, and more. Please refer to the main paper for more details. Now, we showcase the applications. First is appearance interpolation. Given the source view on the left, our method can smoothly transition and generate high-quality images based on the reference image on the right. You can see the Brandenburg Gate transition from a sunny day to a dark, overcast sky. Now, we show the transformation of the Trevi fountain from day to night. This is a demonstration of the appearance change of the Sacré-Cœur Basilica. It's worth noting that the left image is actually a filtered version, not a weather-induced change. However, it can be observed that our method is capable of performing smooth interpolation and high-quality rendering. Now, we showcase some high-quality real-time rendering results, where the appearance continuously interpolates as the camera pose changes. Here is the Sacré-Cœur. Here is the Brandenburg Gate. Here is the Trevi fountain. Finally, we present an example of explicit sky editing and novel appearance rendering. As you can see, the clouds in the sky display the text VR 2025, while the building's appearance also changes with the sky's color. Thank you, everyone, that's all for my presentation. Thanks for listening.